Władysław Sierpinski was a Polish mathematician born in 1882, well known for his contributions to set theory and topology. He is recognized for the discovery of the Sierpinski triangle as well as the Sierpinski numbers. Sierpinski numbers are values of k in the general expression for a Proth prime, k times 2 to the n plus 1, where k and n are positive integers. Sierpinski proved that there are infinitely many odd integers k such that for all values of n, every term is composite, or not prime. Values of k for any value n that yield no prime numbers are known as Sierpinski numbers. The Sierpinski problem asks for the smallest of these numbers. In 1962, American mathematician John Selfridge proved that 78,557 was a Sierpinski number. He found that there existed a covering set, or a set of prime numbers, such that every term produced by 78,557 times 2 to the n plus 1 had a factor in this set. The covering set for 78,557 consists of the primes 3, 5, 7, 13, 19, 37, and 73. Selfridge posited that any value produced by 78,557 times 2 to the n plus 1 would always have at least one factor in this set, making it a Sierpinski number. To demonstrate this trend, I will present a few examples. As we know, 78,557 times 2 to the n plus 1 will always be composite. When n is equal to 1, the value is equal to 157,115, which is divisible by 5, a member of the covering set. When n is equal to 2, the value is 314,229, which is divisible by 3, also a member of the covering set. When n is equal to 3, the value is 628,457, which is divisible by 73, also a member of the covering set. As you can probably tell, calculating Sierpinski numbers takes a great deal amount of time, as there are quite literally infinite values you can use for n. When Sierpinski and Selfridge were first investigating these numbers in the 1960s, computational abilities of computers were very limited, and the calculations they could perform were of the most basic level. 78,557 is unique in that it can be mathematically proven to be a Sierpinski number, but the validity of any number lower than that must be checked with brute force methods. Fortunately, computers have advanced enough in their abilities since Sierpinski's time. This allows for numbers to be crunched far more efficiently than they were in the past, and for the existence of global computing efforts such as PrimeGrid or the 17 or Bust project. These projects aim to eliminate possible solutions to the Sierpinski problem, proving that 78,557 is the smallest Sierpinski number. PrimeGrid and 17 or Bust have also inadvertently found one of the largest prime numbers known to man. The ninth largest prime number, 10,223 times 2 to the 31,172,165 plus 1 is a Proth prime, a result of the calculations done to find Sierpinski numbers. It is unique in that it is the only non-Racine prime in the top 10 current largest primes. Racine primes take the form of 2 to the n minus 1 and are significantly easier to verify and find than Proth primes, a reflection of the time and dedication that has been put into the PrimeGrid project. However, even projects like PrimeGrid have their limits. PrimeGrid only tests up to 31,875,742 for n, with the assumption that the validity of any value for k may be found before the superimposed limit. It is possible that 78,557 is not, in fact, a Sierpinski number, but it is very unlikely and improbable. The depth of the Sierpinski problem does not end here. Nathan Mendelsohn in 1976 proposed that 271,129 was the second smallest Sierpinski number, and consequently, the smallest prime Sierpinski number. No possible value of k has been found thus far to prove otherwise, but projects like PrimeGrid are still testing to see if a smaller such number exists. The Sierpinski problem may seem like a meaningless conjecture, but in reality, it provides a deep and interesting study into the nature and functions of prime numbers.